Hi, everybody. Today's lesson is for Friday, April 10th. Just a heads up, this is the last really new content that we have for the course. So congratulations. Next week, we'll be doing most of the time working on project one. I'll maybe post some video, just mini lessons if there's questions about walking through the spreadsheet. And of course, I'll be around in online office hours as well. So let's go ahead and jump to the notes. All right, so intro admin wise, just as a reminder, project one is officially due next Friday. After today's lesson, you should have all the tools you need to work through the entire project. And again, if you're working with a team member, definitely divide and conquer. Just make sure you guys are coordinating via Google Hangouts, Zoom, email, etc. Also, homework 8 and the solution are posted. Again, all problems are optional. This is really just extra practice of those environmental loading problems. Really helpful as you're preparing for the final exam, which was tentatively still scheduled for April 30th. More details to come as we get more information about kind of what's going on in this crazy environment. As a reminder, so thanks everybody. I'm preemptively thanking you for signing on tomorrow, Wednesday, for our synchronous class. That should be a pretty short class. We'll just introduce project one, talk a little bit about some of the feedback from exam two. But remember back, especially to Monday's lesson, where we talked about how the Morrison equation can be used to find the wave force per unit length on the pile. And we did a couple of examples where we calculated the drag and inertial and then combined force at the still water level on one pile, two piles. And particularly when we're thinking about the Morrison equation, we know that this wave force per unit length varies with depth. So depending on Z in the water column, your time or your phase, omega T, and then where you are spatially. So Kx, your wave number times your X position also affect what your wave force is. Today, we're going to talk about sort of how, based on those variables, we can find the time of the maximum wave force at a given location and depth. And we'll also use a method called Simpson's rule to estimate the total force on a pile. And then again, if you're around for online office hours, please feel free to pop in with questions about project one. Happy to talk through any questions you have. So let's go ahead and get started. I'll move this out of the way. And we'll go ahead and talk about, this is big letter F in our notes, which is wave force variation with time. And again, if we think about just the very basic Morrison equation, we just sum up for our total force per unit length, the combination of our drag force plus our inertial force acting on the pile. And we can plug in, 1/2 rho times the diameter times U times the absolute value of U for our drag force plus our inertial force terms. But a key thing to note is that if we plug in for velocity and acceleration in our drag and inertial force, that means that our drag force and our inertial force are out of phase, because our drag force varies with cosine and our inertial force varies with sine. So that means that our maximum total force per unit length is not equal to the maximum of our drag plus the maximum of our inertia. And furthermore, it also means that we might not have FD max or FI max in our total maximum. In fact, that's probably going to be the case where neither of these is a maximum, but the summation of them is the maximum total force on the pile. So how do we find when our wave force per unit length is maximum? There's 3 ways to do this. So 3 ways to find time when Fx is max. So the first way that you can do this, this always works, option 1, is by definition. And if you think back to maybe Calc 2, we know that the max or min of any function occurs when the derivative, and here we're taking the partial derivative of this function with respect to time. So this is the partial derivative when it's equal to 0. And then also, of course, check your endpoints. So we can plug in all of our terms. So put FD, FI in terms of time. And so we get this gargantuan equation with our total force is equal to 1/2 rho CD times our diameter. Plugging in for U, we get pi H over T times cosh of K times Z plus D divided by sinh of KD. That quantity squared times we'll take the cosine of Kx minus omega T times the absolute value of that cosine. So again, we preserve the sign here. So cosine of Kx minus omega T and absolute value sign. That's our drag force plus our inertial force, which is C sub m rho pi d squared over 4 times our x acceleration, which plugging in our equation for that, we have 2 pi squared h over t times cosh of kx plus, sorry, k times parentheses z plus d divided by sinh of k times d. Again, this term is equal to k times d plus d, rated legibly there. And then that whole term is multiplied times the sine of kx minus omega t. So again, we have a time here, time here. If we take the derivative with respect to t, so we can take dfx over dt and set equal to 0 and solve for t. Perfectly acceptable and really sort of very elegant, beautiful way to solve the problem. Other ways to solve it. Another way that is also perfectly acceptable and will give you the right answer is what I like to call brute force. Or another way to think about this is plotting. So you guys maybe have been working in MATLAB or Excel in your waves classes. And so you can set up a spreadsheet or you can set up a MATLAB file. And then you can vary t and find when either fx is a peak. So you can do that either by plotting or look at trends. If it goes from increasing to decreasing, you know that it has to have reached a peak at that moment. So that's another perfectly acceptable way to find when your wave force is maximized. But the option that we'll talk about in a little bit more detail and that maybe would be useful for your project is option 3. I guess to be consistent, we should call B option 2. And option 3 is to set up an Excel spreadsheet. And you can use the tools that we have computationally to solve for when this is a maximum force. So I'll talk through the method and then I'll sort of walk through on a screen share. So the first thing we want to do is input all variables. So this would be like wave properties. pile characteristics, etc. And then basically calculate your total force per unit length, and then eventually your total force on the pile, which we'll talk about in a moment. So once you have that total force, you can set up solver in Excel. And you might have already set this up in your class, in a different class, but if you haven't, you can go to File, Options, Add-ins, and then you can click the Solver add-in, and then click Go. And then once you're there, you have to check the box. There's like 4 options, and you check the box for Solver add-in. And then you click OK. And that should install Solver in your Excel on your laptop. Once you have Solver installed, if you go to the Data tab in Excel, you should see an option to click on Solver. And the way that we can solve this is you can set your objective cell. And for us, we'll be using either Fx, kind of for an example, or for the project, you want to use the total force, Ftot. And the objective we want, so it'll say 2, and you can click that you want it to be a maximum. There's also options to sort of do minimum, other things. I like to set up constraints. This isn't necessarily needed, but you can do that. Sorry, before we get to constraints, the thing that we change, and you can select the cell where you have time. So we're changing time so that our total force is a maximum. And then again, the constraints that I like to input are to keep my time greater than or equal to 0, and less than or equal to my wave period. So it should reach a maximum 1 time over a wave period. It actually should reach it sort of twice. Once will be a negative, so sort of going the other direction. And then you can click Solve and keep Solver solution. I like to use, I think it's the evolutionary method. Sometimes I have issues with the other ones, but double check me on this. We'll walk through actually right now, and sort of I'll show you how we can walk through this. So I'm going to go ahead. All right, so I'm sharing my screen now. Sorry, I paused for just a moment to make sure that I could show you how to actually add the Solver add-in. So again, if we want to set up Solver in Excel, if you don't have it already in your Excel spreadsheet, again, that'd be by clicking the Data tab. You can go to File, and then you can go to Options. And if you click on Add-ins over here, you should find a way to manage Excel add-ins. And so let's go ahead and click on the Solver add-in here in this list. And let's go ahead and click Go. And now I have this box, 4 boxes pop up. I just want to check mark the Solver add-in and click OK. And it'll go ahead and install that add-in into my Excel. And so now if I click on the Data tab, I see I have the option to click on Solver here. So let's go ahead and click on Solver. I've already sort of set this problem up, but basically what I've done is I've set my objective, which is my objective cell is the cell that I want to optimize. For that, I have the absolute value of my total force, which I calculated using Simpson's rule. I could make that F sub x at the still water level. Note that that doesn't always occur at the same time. So your maximum force at the still water level might not be the same as your maximum total force. So I like to take this maximum total force. I'm changing the value of cell J4. That's going to be J4 is my time. And I can start out with time is equal to 0, but that's what I'm changing the cell value. And again, I'm keeping my cell J4 is less than or equal to my wave period, which I've defined in H4, and it's greater than or equal to 0. So you can add in these constraints by clicking add constraint and kind of typing in the constraints for your cells. Again, you can select a solving method. I like to use evolutionary, but you can try these other ones out too. And then let's just go ahead and click solve. And it's thinking, still thinking. All right, sorry for the delay there. I think it had a problem because I was sharing my screen, but after some thinking, we get this answer where we can say keep solver solution, or you can restore original values. I like to keep the solver solution because that should be your maximum time, and we click OK. So now you can see that my absolute value of my force is a different number that's bigger. And if we scroll up, we can see the time that this happens at. So that's how you can use the solver in Excel. Hopefully you can use that on your projects to find the time of the maximum force. But as a note, as I mentioned, and as I just kind of demoed in solver, sort of this will be item number 3, note is that we care more as engineers about the total wave force, F tot, than we do the force per unit length at a given depth. So again, in your project, make sure that we want to maximize your maximum total force. But the question remains, how do we find the maximum total force? How to find F tot. So let's go on to a different page. I'm going to slide these notes up, slide this down. Up here. And let's talk about big letter G, which is the total wave force. And wave variation with depth. So if we think about any depth Z, we have U, our acceleration, and therefore our wave force per unit length varies. Due to the term, this is called K sub X in your waves EN 475 equation sheet. This is equal to the cosh of K times Z plus D over cosh of K times D. So as Z becomes closer and closer to negative D, this term will become smaller and smaller. So again, we decrease, moving towards the bottom. And so if I were to sketch what this looks like, we would have our water surface here with some force at the still water level due to waves on our pile. This would be Fx1. We'll have another force that is less than Fx1 at some depth, delta Z, below the surface. Here's our pile. Be another force here. Fx3, this is Fx2. Kind of finished drawing the pile here. Here's our water table. Maybe the pile goes above the water surface. But again, our forces are only below the water surface. And then we have fx4, which will be a little bit smaller. And then finally, a force acting at the seafloor, fx5. And you can have lots of these forces. So if I connect these, it might look something like this. And I have some weird function that I really want to take the area of so that I can get the total force acting on the pile. The only other thing I wanted to find here is this is the total water depth. So again, the total force is equal to the area under the curve. So our curve defined by these different values of lowercase f sub x. When you think area, think integration. So this requires integration. My function of f sub x over my depth. So from z equals 0 to negative d. But if you don't want to do the integration of this really long equation that we wrote up here, Simpson's rule is a really powerful way to approximate the total force. So this will be number 3. As a good approximation, we can use Simpson's rule. And Simpson's rule is just a method of numerical integration. Basically, it's kind of like trapezoidal rule, where we're going to say we can assume that each of these segments are regular shapes like rectangles or trapezoids, and we can weight them appropriately and get a really good estimation of what the actual value of this integral is without actually having to take the integral. So this is how Simpson's rule works. Step 1 is to divide your total length into n segments. And note that then your delta z, so each segment thickness is equal to your total depth divided by n. So this will be segment width, delta z. Step 2 is to find the values of your function. In this case, that's f sub x, but really it's just your function of interest at segment boundaries. Note that you'll have n plus 1 boundaries. So if we take an example as the sketch above, we've divided this into 1, 2, 3, 4 segments, and we have, so n equals 4, and we have 1, 2, 3, 4, 5 segment boundaries. So we have to find the values of f sub x at each of those 5 points. So for example, at z equals 0, z equals negative delta z, z equals negative 2 delta z, all the way until z equals negative d. So we're going to evenly space each of our segment boundaries. And then Simpson's rule, the definition in step 3, we have Simpson's rule, which states that the total force, F tot, can be approximated, and this is going to be in units of pounds. F tot is equal to our segment width divided by 3, this 3 is always true, times fx1, so our first value at the outer boundary, plus 4 times fx2, plus 2 times fx3, plus 4 times fx4 plus 2 times fx5. And you keep repeating this 4, 2, 4, 2, 4, 2 pattern until you have to end on a 4. So plus, keep repeating the pattern. So 2 times fn minus 1 plus 4 times f sub n. So this would be whatever your number of segments is, plus that other boundary, 1 times f sub n plus 1. Another way to write this in kind of shorthand is using summation notation. So we can say that delta z over 3 is equal to the summation from I equals 1 to n plus 1 of the Simpson multiplier sub I times fx sub I, where SMI equals our Simpson multiplier, which is equal to 1, 4, 2, 4, 2, 4, dot, 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 4, 1. So you have to start and end on ones and then just keep repeating 4, 2, 4, 2, 4, 2, 4. So this is our general equation. Please note for this class, 4 segments is plenty if you're doing it by hand. So that'll be number 4 for this class. 4 segments is enough. So we can simplify this equation and we get that f tot is equal to delta z over 3 times fx1 plus 4 fx2 plus 2 fx3 plus 4 fx4 plus fx5. And our segment width, z, will always be delta, our depth, over 4, if we use 4 segments. If you're setting this up in Excel, and I'll step through that in a moment, use as many segments as you want, really easy to sort of drag and drop, and I'll kind of show how those equations work. But definitely it's useful, especially for the project, to make an Excel spreadsheet. But let's go ahead and do a quick example by hand first. And then I'll sort of poke around my Excel spreadsheet and show you how I set up some of those wave force calculations. So this will be number 5 is our example. Get on the page here. Focus. Cool. So our example, let's say that we're given kind of a sketch, like a free body diagram almost of a pile. So we have, here's our pile, 1, 2, 3, 4. We know fx1 is equal to 569 pounds per foot. The force here is equal to 423 pounds per foot. The force here is equal to 330 pounds per foot. Then we have a force of 278 pounds per foot. And then finally, a force of 261 pounds per foot. Finish out kind of sketching the pile. This is the floor. And this is the water table. We know that our depth D is equal to 90 feet. And we want to calculate the total force and the location at which it acts, which we'll share that equation as we go through the example. So the first kind of thing you like to do is I like to find my delta Z value. So we have 4 segments with 5 values of f sub x. And so this means that our delta Z is equal to 90 feet over 4. or delta Z is equal to 22.5 feet. Even when I do this by hand, again, if you're in Excel, you're sort of in a perfect place to make a table. But even when I do this by hand, I like to make a table to organize, my Simpson multiplier, my location, my depth, and my force at that depth. So I'll have a column for Z, which will be in units of feet. I'll have a column for my force per unit length, F sub X, which will be in pounds per foot. I'll have a column for my Simpson multiplier, which is just our index, SM sub I. If you're doing this in Excel, it's helpful. You can take F sub X times Simpson multiplier. So this column times this column. And then you can also take Z times Fx times Simpson multiplier. That'll help in the location, the calculation of your moment. This is if you're doing it in Excel. It's kind of easy to have that drag and drop, and I'll show that in a moment. But if you're not doing it, we only have to worry about these first three columns. So again, our 4 segments are defined by 5 endpoints. We have Z equals 0, Z equal negative 22.5, 2Z is equal to negative 45, 3 delta Z is equal to negative 67.5, and then finally our negative D, which is 90. We know the value of our function at each of those locations. So just reading these in, at Z equals 0, F sub X is equal to 569 pounds per foot. Then we have 423 pounds per foot, 330, 278, and 261 pounds per foot. And then our Simpson multiplier will just always follow that pattern of 1, 4, 2, 4, 1. And if I want to find the total force, I know that F tot is equal to delta Z over 3 times Fx1 plus 4 Fx2 plus 2 Fx3 plus 4 Fx4 plus Fx5. So plugging in numbers here, this is equal to 22.5 feet over 3 times 569 pounds per foot plus 4 times 423 pounds per foot plus 2 times 330 pounds per foot plus 4 times 278 pounds per foot plus 1 times 261. Again, all of those were in pounds per foot. So we have feet cancel out and we're left with a total units of pounds. If I take this, this will equal 4,294 pounds per foot. And just as a note, if you're doing this in Excel, we're going to take a lot of sums. That should equal the sum of this column. So this is 4,294. If I just sum up the Simpson multiplier times F sub X. Multiplying that times delta Z over 3, I get that this is equal to 32,205 pounds. Or I can simplify a bit, just convert this to kips. We get 32.2 kips is my total force. The second question asks us to show, find the location at which this acts. And the definition here, we can kind of use moments. Let's use moments about the still water level. So the location, we can find Z resultant, which is equal to the summation of Z of whatever index we're considering times the corresponding value of the force per unit length times the corresponding Simpson multiplier divided by the summation of Fx sub I times Simpson multiplier sub I. Plugging in numbers here, we get that this is equal to 0 times 569 pounds per foot times the Simpson multiplier is 1. That'll cancel out. Plus 4 times 423 times the Simpson multiplier is 4, so the depth is negative 22.5 feet, plus the depth is negative 45, plus my value is 330 pounds per feet. Sorry, this is times. Times my Simpson multiplier of fx3 is 2, plus 2 more to go. We have negative 67.5 as my depth, times 278 times 4. And then finally, we have plus negative 90 times 261 times 1. That's my numerator. Another way to do that, it's easier to do this in Excel because you can just take z, so 0 times 569 times 1, negative 22.5 times 423 times 4, etc., and then just take the sum there. And then we'll divide that by the summation of f sub xi times our Simpson multiplier I. Again, we've already found that as 4,294 pounds per foot. The units of this will come out to be feet times pounds per foot. So we have basically pounds divided by pounds per foot. So feet goes back to the top, and so the location is in unit of length. So that's a good sign. So I can go ahead and calculate these, and I get that my resultant is equal to negative 38.7 feet. And this negative side means that it's below the still water level. And so this is really the last thing you need to calculate how the wave force will impact your pile on the project. I'm going to switch back to the Excel sheet and just sort of walk you through the calculations that I made to find what this total force is. All right, so we're back in the Excel spreadsheet. I highly recommend setting up something like this for your project. It can be really helpful and also really easy if there's a mistake, just to kind of correct an equation or change a number. Here are all of our wave properties, so things that aren't changing. For this project, our depth is 80 feet, the wavelength is 500 feet. With that, we can calculate the wavelength, omega, and period. We can assume that x is equal to 0. I set an arbitrary time of 2. Our pile diameter is 3.5 feet. I think our thickness is 3 inches. Anyways, calculating the wave force, I can go ahead and I've actually calculated Simpson's rule using a lot of different segments. So I have 20 segments, 21 values of my function. And for each value, so at 100% of the depth, z plus d, so z equals 0, z plus d is 80. I can calculate that kx value, so cosh of k times z plus d divided by sinh. Our current is always going to be 0, but I keep this here, especially because the second project, we talk a little bit about what happens when you add in a current. We can calculate u due to the wave based on the equation, sort of, we have hard-coded in some values with t, our wave height, etc. The total force is the addition of the current plus the wave, and then you can take the absolute value. So that's what you can use to calculate your drag force. I can also calculate my acceleration again using that equation, which is this is what it looks like in Excel form. Sort of gross, but just be careful when you plot it. That'll calculate your inertial force. Adding these two together, you get your total force per unit length at the still water level. As I mentioned, I've done this in 20 segments, so that's why we have 1, 4, 2, 4, 2, 4, 2, 4, dot, 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 up to 1. And then I have the addition of my total force, and then I take the absolute value, because if it's negative, that just means it's going in the opposite direction. So again, when we maximize this, a negative value is still fine. And the summation here, you can take the sum product is a really helpful thing to know. So I'm taking the sum product of f sub x times Simpson. So taking the sum product of column L, which is f sub x, and then my Simpson multiplier is m. And then you can take delta z, which I've defined in column B27 as 4 feet, divided by 3. You can also do that for your moment location. So I divided this into the numerator and the denominator. Here, the numerator you can calculate using the sum product of z times fx times your Simpson multiplier. So that'll be your numerator. Your denominator will be just the sum product of f sub x times Simpson. It's different here because I've multiplied times delta z over 3 when I calculated the total force. And then the moment is just your numerator divided by your denominator. So this is how I set up my Excel spreadsheet. You're definitely welcome to set it up any way that is making sense to you, and also happy to talk through this in office hours. But again, this is all I have for you guys. I think next week, let's just plan on checking in about the project. Have a wonderful weekend and looking forward to talking soon.